Good morning, student. Today our topics are number 1, concept of electric potential, number 2, potential difference, number 3, electric potential due to a point charge, number 4, equipotential surface, number 5, energy of a system of 2-point charges. Before this topic, first we define electric field. Electric field due to a charge q at a point in a space is given by the force that unit positive charge would experience if placed at that point. It means there is a source charge which is q and we put a test charge, that is q naught, which is positive charge, and that charge experienced some force due to source charge q, and the electric field is given by F by q naught. If the positive test charge q naught is unit, then electric field is equals to force experienced by the test charge. Okay, now you know by Coulomb's law, the force is given by 1 by 4 pi epsilon naught q naught by r square, where r is the distance between two charges. One is source charge and another one is test charge. Now, the electric field is given by 1 by 4 pi epsilon naught q naught by r square, because q naught is unit, so the electric field is given by E equals to 1 by 4 pi epsilon naught q by r square. Student, remember here q naught, which is a test charge, positive test charge, and that q naught is unit. That's why q naught is equals to 1, and that's why E is given by 1 by 4 pi epsilon naught q by r square, and the unit of electric field is Newton per Coulomb. Now we are start electric potential. Electric potential is also known as electrostatic potential because we are study rest charge. Okay, so the electric potential at any point in the electric field, the amount of work done in bringing a unit positive test charge from infinity to that point without acceleration. That means you want to bring charge in electric field, so you have to do work, and electric potential is given by V equals to work done divided by charge. Here work done is given by W, and charge, which is unit test positive charge, is given by Q naught. Now if you know that Q naught is unit, so V equals to work done. So V equals to work done. Now you know that what is work? Work is force into displacement. Now so the V is force into displacement, but you bring unit positive charge from infinity to given point in the electric field. That's why the electric potential is given by infinity to integration of infinity to a f external force into dr, or equals to infinity to given point and f e dr. That means force due to electric field, and minus sign here denote that the work done against the electric field. So that's why V is given by minus integration of infinity to a f e into dr. The unit of electric potential is volt or joule per coulomb, and the dimensional formula of the electric field, electric potential, is ml square t minus 3 a minus 1. Now electric potential is a scalar quantity, and that electric potential can be positive, negative or 0. This depends on the sign and the magnitude. So the electric potential is given by minus infinite integration of infinity to a e f in f e into d. Now our next topic is electric potential difference. First we define what is electric potential difference. It is a difference between 2 points of electric potential. Okay, now here electric potential difference in any electric field of point P and Q is equal to the difference of BP and BQ. In figure, Q is a source charge, and due to this source charge there is an electric field, and we want to find out electric potential difference between P and Q, which are the point in the electric field. Suppose VQ and BP are the electric potential at Q and P respectively, then the electric potential difference is given by del V equals to Vp minus Vq. If WQP is the work done by an external force in moving a unit positive charge against the electrostatic force from point Q to P along any path, then electric potential difference is given by WQP by Q naught. Electric potential difference is also a potential, so the unit of electric potential difference is same as electric potential, that is volt, or you can write joule per coulomb, and also the same dimensional formula like that ml square t minus 3 a minus 1. Let's try to understand by an example. The example is the potential difference between 2 points is 20 volt, and how much work will be done in carrying a charge of 400 microcoulomb from one point to the other points. Student, we know that V equals to W by Q naught, where W is a work done and Q naught is a unit positive test charge. Now here the value of V is 20 volt and Q naught is 400 coulomb. And first we have to convert this 400 microcoulomb into coulomb. Now that's why we write 400 into 10 to the power minus 6 coulomb. So the W equals to V into Q naught. The value of V is 20 volt and the value of Q naught is 410 to the power minus 6 joule coulomb. So the work done is 8 into 10 to the power minus 3 joule. Now our next topic is electric potential due to point charge. For this, first we consider a point charge, point positive charge Q placed at O. Okay, now and we calculate its electric potential at point P, and the test charge point is Q naught at point P. For this, first we consider a very small distance, that is small dx. Now here the distance between O to A is x and O to P is r, and the very simple, by the Coulomb's law, electrostatic force acting on the charge Q naught at A is given by what? It is F equals to 1 by 4 pi epsilon naught Q into Q naught by x square. And the force F acts away from the charge. Okay, that means the force which is given by Coulomb's law between O and A is F equals to 1 by 4 pi epsilon naught Q into Q naught by x square. Now let consider a small distance that is AB equals to dx. Now therefore the small distance work done is moving the test charge Q naught from A to B against electrostatic force. So for this the small work done is given by once again force into displacement. Now force into displacement, that means F dx cos theta. Here theta is a 180 degree, that's why the value of cos theta is minus, and the small work done is given by dw equals to minus F dx. Now we calculate total work done from infinity to point P. Therefore, the total work done in moving the charge Q naught from infinity to the point P will be given by W equals to infinity integration from infinity to R dW, that is which is equals to minus integration of infinity to R F into dx, or you can write like that, W equals to minus integration of infinity to R 1 by 4 pi epsilon naught Q naught x square into dx. Okay, so after integration the work done is given by 1 by 4 pi epsilon naught Q into Q naught by R. If test charge, or you can say unit positive charge, is unit, then the potential is equals to work done by unit positive charge, which is equals to 1 by 4 pi epsilon naught Q by R. Here you have to remember unit positive charge, test positive charge Q naught is equals to unit. Now we try to draw a graph between electric potential and distance, as well as electric field and the distance, and try to understand what is the similarity between electric potential and electric field. Now electric potential is given by 1 by 4 pi epsilon naught Q in Q by R. That means the 1 by 4 pi epsilon naught and Q, that quantity is constant, so V is directly proportional to the 1 by R, or you can say V is inversely proportional to the distance. Okay, and you know that electric field is given by 1 by 4 pi epsilon naught Q by R square. Once again, Q by 4 pi epsilon naught is a constant quantity, so electric field is directly proportional to the 1 by distance square, or you can say that inversely proportional to the square of the distance. When we draw a graph, potential versus distance and electric field versus distance, we get like that nature. Okay, and there is a one point where both are coincident. So what is the point? This point is when the distance r is 1. It means at r equals to 1, or you can say unit, for r equals to u, for unit is V and E are both are equal. It is a very important according to your exam. Now our next topic is equipotential surface. First we define what is equipotential surface. So any surface that has same electric potential at every point on it is called an equipotential surface. It means in the whole surface the electric potential is same. That kind of surface is known as equipotential surface, the surface of a charge conductor on the equipotential surface. Okay, now we try to show some different equipotential surface. First equipotential surface is generated by two equal and opposite charge. That means there is a positive charge and there is a negative charge. That means that surface is shows by two equal and opposite charges. Second one is equipotential surface for two same and equal positive charges. Like next equipotential surface for a uniform electric field. They are the line of forces and they are equipotential surfaces. Our next potential surface made by single positive charge. Now there is equipotential surfaces and they are force line. Okay, student, there are some very important points according to equipotential surface. Number one, no work is done in moving a test charge over an equipotential surface. It means any charge want to move on that equipotential surface, there is a no work done. Okay, so no work is done in moving a test charge over an equipotential surface. Second point is electric field is always normal to the equipotential surface at every point. Okay, see this equipotential surface and they are force line, and all the force line is perpendicular to equipotential surface. And third point is no two equipotential surface can intersect each other anytime. Now our last topic is potential energy of a system of 2-point charges. It means there is a system which is made by 2-point charges, that is Q1 and Q2, and the electric potential energy of these system, or you can say the electric potential energy of system of 2-point charges is equal to the work done. The charges, or you can say equal to the work done in the bringing the charges from infinity to closer each other to from the system. That means you see here there is a system of two charges Q1 and Q2. They are placed at point P1 and P2, and you want to calculate the potential energy of this system. Then the total potential energy is given by total work done from these two charges bring from infinity to that place. Okay, now for this let calculate of the potential energy of this system. So first let P1 point P1 and point P2 where the charges are Q1 and Q2. Okay, first we bring Q1 charge in place P1. Okay, so before charge Q1 there is no charge. That's why when you bring point charge Q1 at that place, so there is no work to the bring the first charge, or you can say uh, bring the charge q, because there is no field yet. So the work against for q1, which is given by w1, is equal to 0. But when you charge q2 bring from infinity to point p2, there is a electric potential due to charge q1. Okay, then the electric potential due to charge q1 at a point p2 at a distance r12 is given by v1 equals to 1 by 4 pi epsilon naught into q1 by r12. So if charge q2 is moved in from infinity to point p2, the work required is w2 equals to potential into charge. Here the potential is due to q1 charge. Okay, so the work done W2 is equals to 1 by 4 pi epsilon naught Q1 by R12 into Q2. So the work done for Q2 charge is given by W2 equals to 1 by 4 pi epsilon naught Q1 into Q2 by R12. So the total work done for this system W1 plus W2 is stored as the potential energy U of the system for Q1 and Q2. Therefore, the total potential energy is given by U equals to W1 plus W2. But W1 is 0 and W2 is 1 by 4 pi epsilon naught Q1 into Q2 by R1 in R12. Okay, so the total potential energy for two charges is given by U equals to 1 by 4 pi epsilon naught Q1 into Q2 by R12. So thank you for joining these classes.